So with these, move this out of the way. So we're going to take a look at a couple different sequences, but before we do that, we actually need to kind of take a step back, and I want to make sure we have a better understanding or a good understanding of something called function notation, okay? It's something I know you guys have seen before and you've worked with before, but I just want to make sure we recognize it because it is another way that we're going to be able to identify these sequences and represent the patterns and the rules that go along with them. So if you guys will probably recognize this. It says consider the function f given by f of n equals 3n minus 7. Now, when we first introduced these to you guys, you probably recognized it more like this. We probably didn't use n, we probably used x. F of x equals 3x minus 7. And we basically, at the time, we told you that f of x is the same thing as y. Okay? Now, this would just be a linear graph. It'd be a line that has a slope of 3 and crosses the y-axis at -7. All right? Now, the reason why this function notation is important, back then it was important because if we could identify, if we said, all right, let's evaluate f of 1. Well, that means you're plugging 1 in for x in your right side. 3 times 1 minus 7. 3 times 1 is 3, minus 7 is -4. So we knew that f of 1 equals -4. Now, that was important because it told us that when x equals 1, y equals -4, right? It put the x and the y values together. It allowed us to know the solution for a specific x value just by looking at the function notation of that equation, right? Now, this can be really beneficial for us because what we're going to do, n is going to represent the number in the sequence, like term 1 or term 2 or term 30. What we're going to be able to do is we're going to be able to type in, we're going to use function notation, and this isn't f times n, it says f of n. We're going to be able to plug in what number we're looking for in our sequence, all right? And by using the rule, we're going to be able to generate what that number is going to be, okay? Now, we won't even have to know all of the numbers in the sequence before it, okay? But we're going to need to understand this function notation in order to do that. So what we're going to do is we're just going to evaluate a couple items using this function, f of n equals 3n minus 7, all right? And I just want you to follow along as I evaluate them, mostly mentally. I'll probably write a few things down. Okay, so it says f of 10. So we want to evaluate f of 10. All right, so f of 10 equals, well, if I'm substituting 10 in for n, that's 3 times 10, which is 30. 30 minus 7 is 23. So f of 10 equals 23. Now this one says f of 10 minus 1. So what we'll do is we'll evaluate f of 10, which is 23. Okay. So f of 10 is 23 minus 1. Well, 23 minus 1 is 22. Okay, now this looks very similar, but it's a little different. Okay, just like with normal order of operations, okay, we'd want to do what's inside the parentheses first. Well, in this case, 10 minus 1 is inside our parentheses. Okay, now it's not f times 10 and f times -1, so you're not distributing this, but we can evaluate what 10 minus 1 is. Okay, 10 minus 1 equals 9. So really what we need to evaluate overall is f of 9. 9 times 3 is 27. 27 minus 7 is 20. All right, last one. F of 5 minus f of 4. So in this case, we need to evaluate both of those functions separately. F of 5 is 3 times 5. 15 minus 7 is 8. So this equals 8. F of 4, that's 4 times 3 is 12, minus 7 is 5. 8 minus 5 equals 3. Okay. So just a real quick taking a look at function notation, making sure we have a good understanding of how that works. The goal later on in this unit is to be able to define our rules, okay? And we'll have practice with this, define our rules to enable to use function notation where we can input what number in the sequence, the term of the sequence in, and what the function is going to give us back is going to be what that solution is in the sequence, okay? All right, let's get back to some actual sequences here. All right, here are the values of the first 5 terms of 3 sequences. All right, we got A, B, and C. I want you guys to take a look at those. For each sequence, describe a way to produce a new term from the previous term. I'm going to give you guys about a minute to take a look at these 3, and on a sheet of paper or on your computer, write down, okay, what you think the way you can produce a new term from the previous term would be. So basically a rule. Write down what you think the rule is to go from one term to the next. All right. Well, it looks like in sequence A, it looks like we're adding 10 each time to get the next term. So I'm going to write down add 10. Okay. In the second one, it looks like we're adding, all right, but it looks like every time we move from one term to the next, we're adding 5 more than the previous. Okay. So I'm going to write down add 5 more each term. And lastly, looks like we add 1, then 2, then 4, then 8. Well, it looks like we're doubling how much we add, or might be, I think it's probably easier to think of as we're doubling each term. Double 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. Multiply by 2. Okay. All right. So we got rules for each of these 3. If the pattern you described continue, the patterns you described continue, which sequence has the second greatest value for the 10th term? All right. So if we were to just continue, which one's going to be the middle, like the middle one? If we go to the 10th term in each of these sequences, which one's going to have the middle value? Well, I'm actually only going to go a few, and I think you're going to see what's going to happen here. All right. This goes 1, 2, 4, 8, 16, 32, 64, 128. And that's only 1, 2, 3, 4, 5, 6, 7. That's the 8th term. This one's going to become, let's see, we're at 50, 75, 105, and then what am I adding this time? 30, 35, so 140. All right, and then this one's just adding 10. 80, 90, 100. All right, well, already the one that started the biggest is not as big, and this is just 8 terms in. Okay, it's just 8 terms in. So this one's going to be the smallest. So A is going to be the smallest. Okay. Now the biggest one's going to be between these two. And if I were to go one more term, I think it'll be pretty obvious which one's going to be bigger. All right. If I go one more term in C, what is that going to be? 256. All right. And then if I go one more term in this one, that's going to be 180. Well, this just leapfrogged pretty quickly. All right. If we go one more term, this one's still going to be the middle term. So this is our biggest. C is going to be our biggest. A is going to be the smallest. B is going to be the middle value there. Okay. It's going to be the one in the middle. So you can see, but the different patterns, all the different sequences here, all give us some different levels of how quickly things move up and down. Okay. Which of these could be geometric sequences? Well, only one of these involved multiplying by the same number each time from one term to the next, and that was C. Okay, so C is the only one that can be a geometric sequence. Now, there is a way we can put a rule together where we're actually multiplying things together and to find our pattern in B, but it's not going to be the same thing that we're multiplying from first to second term, second to third term, third to fourth term. Okay, it won't be the same number. It has to be a constant that we're multiplying by that is a growth factor. So the growth factor is going to be the same. This is kind of a bonus add-on part to this, but would it be possible to have a sequence of numbers that's both? Well, I'm going to save that question for in just a second here. All right. Now, the type of sequence that we're going to talk about, I'm actually going to go down to the definitions, then come back. The new sequence we're talking about is something called an arithmetic sequence. Okay, it's a sequence which each term is the previous term plus a constant. Okay, a previous term plus a constant, which is different than our geometric sequence, which is a sequence in which each term is a constant times the previous term. All right. So the two examples were like we had up here. A represents an arithmetic sequence because we're adding 10 each time, whereas C is a geometric sequence because we're multiplying by 2 each time. Now, my question I was going to ask previous is there a sequence that can both be arithmetic and geometric? Okay, can it be both? Now, typically when we're talking about things being both, where you have a similarity between adding and multiplying, you probably need to look at things that are either being added by 0 and multiplied by 1. Okay, so here, take a look at this sequence. In fact, we used this sequence the other day. This sequence is actually one that can be arithmetic and geometric. Okay, we could add each term by 0 and we could multiply each term by 1. Okay, that's one that would work. We actually could do any one where you have a constant number there, where you're adding 0 and multiplying times 1. Okay, so there are sequences that work for this. We could do zeros. We could say adding by 0 and multiplying by 0, but that'd just be straight zeros across. So there are a few examples that this does happen, but they're very unique looking in how the sequences go, and they're very constant. Okay. All right, so here's situation. We got Jada and May are trying to decide what type of sequence this could be. Jada says, I think this sequence is geometric because in the value column, each row is 3 times the previous row. And May says, I don't think it's geometric. I graphed it and it doesn't look geometric. Okay, so I'm going to go ahead. I'm going to sketch a graph just right in here, so we can kind of see what May was looking at. So if we got a little graph, and I'm going to go 1, 2, 3, 4, 5, and then the values go, let's say 5, 10, 15, 20. All right, so in term number one, which is right here, it only has a value of 2, so that's just above the axis. Term 2, it goes up to 6. And term 5, 1, 2, 3, 4, 5, goes up to 18. Okay? Now, if you guys remember, when we did our geometric sequences, those graphs started really low and then got big real fast. Okay? This graph looks more like a line. Okay? So I think what's happening here, we're missing some terms. We're missing term 3 and 4. Okay? But what's happening is this actually is representing an arithmetic sequence because arithmetic sequences go up at a constant rate. They represent linear graphs, okay? Because they go up constantly. Whereas the geometric sequences go up exponentially. They either exponentially grow or exponentially decay. Okay, so the person that's right here is actually May. And the reason why she was able to notice that is because the graph didn't go up as fast as it should if you're multiplying by 3 every time. Okay. So how are they alike and different? Well, they are alike in the fact that when you're adding a constant number or you're multiplying by the same number, the graphs do both increase, okay? Whether it's a constant increase with a line or it's an increase exponentially, okay? Now again, the sequence wouldn't include all of these points, it would just include certain points along the way, okay? But we would be able to identify that path that the graph would follow. So they both go up. The difference is they go up at different rates, okay? Whereas the arithmetic one is constant, the line or the graph that represents our geometric gets steeper as we go. Okay, we could say the same thing about the graphs that go down, all right? Again, the geometric ones change rates as they go down, whereas the arithmetic ones, where you're adding a negative number or subtracting the same number every time, it's going to be constant in how it decreases. Okay. So many sequences start with the terms 2 and 8. I want you guys to give these a try. I'm going to give you 2 minutes. It says find the next two terms of the arithmetic sequence 2, 8. So this is the one that's an arithmetic sequence. So think about what that means. Number 2 says find the next two terms for the geometric sequence. Okay. And then 3, find the two possible next terms for a sequence 2, 8 that is neither geometric nor arithmetic. So think about another rule you can use to go from 2 to 8 and then apply that rule to the next two, right? But make sure it's not a geometric or arithmetic one. And there's actually a lot of examples you can use for this. But I'm going to give you guys a couple minutes. Try and do this on your own, and then we'll come together and we'll talk about the patterns that I thought of. All right. So the arithmetic sequence, remember, this is when we're going to be adding or subtracting the same number from one term to the next. So I'm just going to identify, what am I adding to 2 to get to 8? I'm adding 6. So I'm just going to keep adding 6. So 14 and 20 would be the next two terms. Okay. Now your geometric sequence, that's what you're going to multiply. So to go from 2 to 8, I have to multiply times 4. So I got to keep multiplying times 4. 128. Okay. Now you can see that jumps up a lot faster. Now 3, there's more you could, I'm going to come up with one here, but you guys could have come up with multiples. I could have said multiply, take the previous number, multiply times 3, and add 2. So 2 times 3 is 6, plus 2 is 8. 8 times 3 is 24, plus 2 is 26. 26 times 3 is 78. 78 plus 2 is 80. Okay, and then I could keep going. This is just one example, okay? It is not, again, this morning I think the example I used was, I'm going to add 6, then I'm going to add 12, then I'm going to add 18, and I just kept adding 6 more onto what I'm adding to the next term. All right. Both of those would work. There is an infinite number of ways to do number 3. Okay. So the key to this is, I just want you guys to have a better understanding of the difference between arithmetic and geometric sequences. Just remember, arithmetic sequences, you're adding something each time. And again, you could say subtracting, just like with our geometric sequences, dividing by 4 is the same thing as multiplying times 1/4. We want to be able to identify what we have to multiply things by, because that's our growth factor. Kind of the same idea with our arithmetic. I want to know what you're adding each time, okay? And what you're adding could be a negative. If we're subtracting 2 each time, well, that's the same thing as adding a -2. All right?